Dr. Michael Stenstrom received a PhD and Masters of Science in Environmental System Engineering from Clemson University. He is a distinguished professor of Civil and Environmental Engineering Department at UCLA since 1977. He has received many prestigious awards, including the American Academy of Environmental Engineers, AEESP, Best Doctoral Dissertation, wow, Frederick Portland Research Medal. He has contributed to the publication of 220 total journal publications. Please help me in welcoming Dr. Stenstrom up to as he speaks on stormwater pollution and infiltration.
So hello, everyone. My name is Mike Stenstrom, and I'm a professor at UCLA. I've been here many, many years, almost forever, it seems like, and my area is environmental engineering. I've worked on a lot of different environmental engineering projects, all of which contribute to sustainability and improving the environment. So today, I'll talk briefly about some of my previous research on stormwater management, which relates to infiltration of stormwater. Over the years, since about 1985 or so, I've been working on stormwater as part of my work. This is the PowerPoint I've prepared for today. It talks about a type of stormwater pollution and how we can control it by infiltrating it into the land. It's useful for two purposes. One is that some of that stormwater we can beneficially reuse and reduce our load on imported drinking water. And the other valuable contribution is it reduces the amount of pollution that runs off to receiving waters like the ocean. So stormwater runoff, it's been a problem for many years. We've known about it. It contributes to pollution and is generally considered non-point source pollution. We've worked on various aspects of it, such as trash on beaches. As a non-point, it requires many control locations. That makes it difficult. It's not possible to build a big, large treatment plant as we do with wastewaters. Also, stormwater flows are episodic. They range from zero at dry times to peaks much larger than wastewater flows. So a 1-inch storm in Los Angeles, west side, would be 30 days of flow at the big treatment plant. And so we don't get much rainfall here. We get about 15 inches per year in about 10 events. I say this year has been an extreme anomaly because we've had a lot of rainfall. And the previous year we had a lot of rainfall. Before that, we had droughts. So it can go from just a little bit to too much. And so this is the example I was talking about. A 2-inch rainfall event in West Los Angeles would create approximately 30 days of flow for the Hyperion treatment plant. And so it's not possible to build treatment plants to treat stormwater. We have to look for other mechanisms. And so storm drains can be flashy. What that means is when the rain comes, the flow can go from near zero to a really large amount very, very quickly. And that makes it more difficult technologically to manage them. So here's a storm drain that's in West Los Angeles. This is close to where I used to live. This is Bayona Creek. You can see it's pretty dry. This is during the winter, but it's during a dry part of the winter. The little bit of water you see in the storm drain is what we call nuisance water. It's usually water that comes from people watering their yards or from cooling tower blowdown or from leaks in pipes and so forth. But you can see there's very little flow there. And look at this white pipe that crosses. That's a water pipe. It's not involved in this other than it helps you see the difference. And so here we see on the right-hand side, stormwater flow. And this was just a couple of hours in the storm. And it was at night, so it was challenging to take this picture. But you can see the pipe that goes across the creek. It's this pipe up here. And you can see here the waves. It looks like people could surf it almost. And you can see there's houses and so forth. And so that's what we have to deal with. It goes from near zero to a very high flow in just a matter of an hour. So it presents major problems to manage, and we need to rely on small-scale solutions, which means that we need to have all these different smaller properties managed in such a way that they retain as much of the water as possible, and when they do discharge, they don't discharge highly polluted waters. And so what that means is that we have to worry about land use. We can't just ignore the land use. We have to worry about what's on the top of the land and so forth. For industries, it means that you capture all of the water in such a way that it doesn't flow into contaminated areas. So you have to cover things up. So we want to reduce the pollution produced by the runoff. We want to capture the runoff in such a way that it can be used beneficially. We want to reduce the peak flow to facilitate capture. It's hard to capture the flow if it goes from zero to a huge amount. There are things we can do so that the flow gradually increases. And one of them is reducing the impervious area. Impervious area, such as pavement, is sort of the enemy of stormwater management. And there are things we can do to reduce the impervious area. And one of them is porous pavements. That can be done in areas where we would normally have concrete or asphalt or something like that. And then we can do small scale capture. For example, you can put rain barrels on the gutters of your house. If you live in a house, you can connect the gutters from the roof to rain barrels, and then the rain barrels capture the water and allow you to use it later. So it serves two purposes. So this is something I've been working on for a long, long time. I first published this paper about 1988. I call it the UCLA tree. My motivation for this were the parking lots at LAX, because I would park my car at Lot C at LAX when I traveled. It's a huge parking lot, and what it had was a tree every so often in a concrete box with a drain to the storm system and a sprinkler head. And so I thought to myself, well, that's not a very sustainable way to manage this. We could build different types of infiltration devices so that we could reduce the amount of runoff, and we might be able to produce some better situations with plant life. So this was the picture I drew and put it in a paper, and it's a tree in a box in a concrete or asphalt parking lot. And we sloped the parking lot towards this infiltration box, and you can see the box is open and the water can flow in. And I put a park bench there, and I put a tree, and then there's an overflow to the storm drain or the storm sewer. Below the grade, you have topsoil and then sand and then gravel or other porous fill. And so what that does is it fills up in the rain, retains a lot of the runoff. And so retaining the runoff, it will allow some of the contaminants to biodegrade, which is a good thing. And the overflow is there in case we have a really, really large rain so that nothing is damaged. So I call this the UCLA tree, and I published it and I proposed it. And it was largely ignored for a long time, but we're finally seeing some action on building these sorts of things. Here's an example of one that's up in Portland, Oregon. And you can see it's a residential street, and there's residential property there. And you can see the curb here. It has these openings that allow the storm water to flow into the grassy area, and the plants can grow. And what this does is it allows the water to infiltrate, that in some cases can help groundwater, but in other cases it prevents the storm water from flowing out into the receiving area. And that's important for a lot of reasons, one of which here in Southern California is bacteria transport to the ocean. You know, surfers don't like to swim in high bacterial counts, and this would have the purpose of reducing those bacteria counts, among other pollutants. So here's one in downtown Los Angeles, and you can see we're finally getting to build these things here in Los Angeles. This grading here is covering a track that would take stormwater from the street into this grassy area. Now, the grassy area allows infiltration, but it also allows biodegradation, because a lot of the contaminants from automobiles, such as oil and grease, can biodegrade. So by just retaining them for a while on the soil, the bacteria will degrade them and detoxify them. So here's one example. Here's another example. And you can see there's a tree here that's growing, and all of this has been replanted. This is the connection to the street. These are rather new for Los Angeles. The one in Portland, Oregon has been there for maybe 15 years or so. And you can see there's also an entrance here for the sidewalk. Here's another view of it. You can see the tall building in downtown. If you're at all familiar with downtown, you can recognize these buildings. This whole street has these green areas. We were successful in constructing a lot of these a few years back with something called Proposition O. That provided $500 million to build stormwater solutions. It was funded by a bond issue. And so you can Google Proposition O if you want to know more about the kind of things the city of LA built. And so here's something that we can build when we don't have much land. And this is a kind of porous pavement. You can see at the end there's a grassy area, but this pavement is really a bunch of concrete blocks set on end, and then soil is introduced into the open areas. And the soil is porous, so when the rain falls on this area, it doesn't all wash off into the ocean. It infiltrates. And the contaminants from the automobiles, such as the oil and grease, can degrade in the soil area and detoxify. So here's another one. This one's in Europe, and I was attending a meeting over there, and I saw this, and I always carry a camera with me. So this is an example of porous pavement. And I think this was sort of a test area here because they only did a part of it. The nice thing about this porous pavement is that you can drive a vehicle on it. Some porous pavements you can't drive vehicles on, but this type of pavement you can. So another way of infiltrating is to improve our rivers. I showed you Bayona Creek, which is a concrete channel, and there's no infiltration from the water in Bayona Creek to the groundwater until you get almost to the coast. But the LA River is a project that we could do lots of infiltration. You might recognize this picture. You can take it from the 10 freeway, and you can see this is during the summer when there's very little flow. And there are entrances such as this one for drainage to the LA River. There have been efforts to kind of restore the LA River, which would also result in more infiltration. So this is more upstream in the LA River. This is up almost to the east end of town, almost to Glendale. And you can see here we have ponded water, and we have wildlife here. We have ducks and stuff, and much more picturesque scene than what the downstream part of the LA River is about. We would like, as much as possible, to extend this type of management to all the property in LA that we could. It's a small is beautiful kind of thing where you could do small projects and you wouldn't have to plan for a $1 billion project. You could do smaller projects, and gradually over time we could improve the environment. So this is the summary. Stormwater is challenging. Capturing it is challenging, and we require new approaches. The conventional wisdom about managing and reducing pollution doesn't work for stormwater. One of the problems is that not everybody owns stormwater. Who owns the stormwater? Well, with point sources, you usually have somebody that can manage a permit. But for stormwater, we have every property parcel that has to be managed. So it's a small is beautiful sort of thing. Small scale solutions exist. They're not terribly complicated. They don't require, huge advanced technologies. They're things that even a homeowner could build. And the solutions suffer from lack of effort. They're there, we can implement them, but construction and funding are needed during times when there's not an acute need. What that means is that when it's not raining, we don't see the need for stormwater management. We need to keep up our efforts. So I've been working in stormwater for quite some time. We've made lots of advances. One of the things that's helping us with stormwater are the droughts, because stormwater is a source of water during droughts. So this is one of the things I've been doing over the years. I appreciate your comments, and this is my email address if you'd like to email me something and ask me a question. Thank you.